Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will continue our discussion of Le Chatelier's principle by taking a look at how changes in pressure or volume affects the position of equilibrium for a given chemical reaction. Now, when the stress that's being applied to a chemical system involves changes in pressure or volume, this effect is mostly applied to substances that are gas in state. But it's not exclusive to that specific physical state of matter. We saw how changes in volume for an aqueous solution affected the position of the equilibrium by changing the amount of solvent in the solution. And so in an aqueous solution, we can think of solvent as the substance that dictates the volume for that specific solution. And so if you have changes in solvent, you have changes in volume for aqueous solution. So let's just say that we have these particles in this little beaker, and the volume of the solution is this amount, whatever that volume is. And so if we evaporate the solvent, that changes the volume of the solution so that the particles become more concentrated. And so when this happens, Le Chatelier's principle tells us that to counteract the stress that was applied, in this case the evaporation of the solvent, the chemical system will shift the position of the equilibrium to favor the side that contains the lesser number of species in that chemical reaction. And so once again here, in this example, we have two particles that are considered reactants and one particle that's considered a product. And so since there's more particles in the reactant side, if you evaporate the solvent, if you change the volume by decreasing the volume, then the equilibrium will shift to the side of the products, favoring the production of the product to help alleviate the stress that was applied. Okay? And so overall, here we have a decrease in volume. And if we have a decrease in volume, the equilibrium will shift to the side that contains the less number of particles. And so we saw the opposite effect when we increase the volume of an aqueous solution. And one way to do that is by adding more solvent. And so if we put some particles here, and let's say that the original volume of this aqueous solution was, this amount. If we add more solvent to this beaker, we essentially increase the volume. And so increasing the volume for an aqueous solution shifts the equilibrium such that the equilibrium will move towards the side of a chemical reaction that has a greater number of particles. And so here in this case, if this is our chemical reaction, and if we were to add more solvent, which increases the volume of the solution, the equilibrium, the position of the equilibrium, will shift to the side that has the greater number of particles, which happens to be, in this case, the reactant side. And so, if this chemical equilibrium was flipped, then the equilibrium will shift to the side of the products, in this case, FeSCN, right? It's always moving towards a side that has a greater number of particles. And so that last example that I mentioned, we just flip this. If you guys can imagine flipping that chemical equation and then applying this same principle, then the equilibrium will shift to the right. Okay. And so we kind of observed how changes in volume affects aqueous solution. And we're going to take that same principle and apply it to substances that are in gas state. And so we first need to conceptualize what an increase in pressure or a decrease in volume looks like. And so here we have a container with a movable piston. And so if you were to increase the pressure, you're going to take this piston and push down. And by pushing down on that movable piston, we inadvertently decrease the volume of that container. And so an increase in pressure decreases the volume of the container as well. And so this is the scenario where we're going from this specific state to this specific state in terms of the volume of the container. All right, and so how will the equilibrium shift when you increase the pressure or decrease the volume of the container? And so here we have this chemical reaction between hydrogen gas and nitrogen gas to produce ammonia. And so let's just say that we have these particles that's placed inside this piston. So I'm just going to go ahead and write it in real quick. So I have 3 hydrogen gases. And then I have 1 N2. And I have 2 NH3s. Okay. And so what we're going to do is we're going to increase the pressure. So this is the stress that's being applied. And we're inadvertently decreasing the volume when we increase the pressure. And so we still have the same number of particles. And so if you look, here we have 3 H2s. We have 2 NH3s. And here we have an N2. Okay. So look at how much volume there is left. So basically these particles are very uncomfortable with an increase in the pressure and a decrease in the volume of the container. And so to alleviate the stress that's being applied on this chemical system, the equilibrium will shift in favor of the side that has a less number of particles. Very similar to what we saw here for the solvent for aqueous solutions. And so since we have 4 particles on the reactant side and 2 particles on the product side, then when we increase the pressure or decrease the volume of the container, the equilibrium will shift in favor of the least number of particles. So the equilibrium will shift in favor of the least number of particles. And so why? Why does that shift in favor of the least number of particles? Here we can go ahead and observe that if we, let me see here. I think I want to use this tool. So if you look at this chemical reaction, if we go in the forward direction, we're going to take 3 moles of H2, 1 mole of N2, and we're going to make 2 NH3. And so we're going to do just that. We're going to take all 3 of these hydrogen gases and 1 of these nitrogen gases, and we're going to create 2 more NH3s. Do you see how the shifting of the equilibrium in favor of the side that has the least number of particles alleviates the stress? There's more room for these particles to move around compared to, the previous example. Okay, and so I'm just going to go ahead and draw another piston over here just to kind of look at the transition that I erased. Okay. And so here we had 3 H2s, 2 NH3s, and 1 N2. So notice how it was very tight and uncomfortable. Okay. And so hopefully you guys can understand with this visual drawing why the equilibrium shifts towards the least number of particles. Okay, so I'll go ahead and add in some more notes here on my PowerPoint, and I'll post that with this PDF, with this PowerPoint on Canvas. Okay, so let's go ahead and look at another scenario. Once again, we're looking at how changes in pressure and volume affects the position of the equilibrium for particles that are in gas state. However, this time we're going to look at a decrease in pressure or an increase in volume. So how do those stresses affect the equilibrium, the position of the equilibrium? So whenever we're decreasing the pressure, we want to imagine that we're taking our hand off of the piston and allowing the piston to rise. So an analogy to this is like a balloon. And so if you take a balloon and you squeeze it, you're applying pressure on the system. But if you let go of the balloon, then you decrease that pressure. And when you decrease the pressure of the balloon, the original shape of the balloon will be reformed. Thereby the volume of the balloon will increase. And so if we decrease the pressure and increase the volume, how will the equilibrium shift? And so this is the scenario where we're actually starting from the container that's on the right hand side, and we're moving to the container towards the left. And so this is an example of a decrease in pressure. Actually, let me do that in black. So here we have a decrease in pressure and an increase in volume. Okay, as we go from right to left. And so once again, we're going to work with the same number of gas particles. And so here I have 3 3 H2s, 1 N2, and NH3. Okay. And so if we're starting, if the equilibrium looks like this, and if we increase the volume by decreasing the pressure, allowing the piston to move up, what's going to happen is that these particles gain more room to move around. And so since there's more room to move around, then the equilibrium will shift to the side that has the greater number of particles. And so if we're looking at this same, actually let me just copy this so I don't have to rewrite it. Okay. And so let me erase this, let me erase this, let me erase this. Okay. So if we're looking at this equilibrium, notice how there's more particles here on the left-hand side, the reactant side, and there's less particles here on the product side. And so if you increase the volume by decreasing the pressure, then the equilibrium will shift in favor of the side that has the side that has more particles. So equilibrium will shift in favor of more number of particles. And so if we take the NH3 and if we remove this, we get 3 more hydrogen gases if we follow the stoichiometry. And we also gain an extra nitrogen gas. Okay. So notice that the pressure that was observed here when the equilibrium shifts to the side that has a greater number of particles, it's trying to get that same pressure back. Okay, so you guys can think about it like that. Okay, so there's more room to move around. Equilibrium shifts in favor of side that has more particles. Okay. And so we can think about this like trying to get back the original pressure. So for example, let's just say that you're in your room and you're used to, 77 degrees. That's your comfort temperature. This might be a really bad analogy, but let's work with it. And so let's just say that, the temperature is going to, suddenly increase, and what you want to do is you want to lower the thermostat so that you're back at 77. And so that's what's happening in this scenario where this equilibrium is used to a specific pressure. And by lowering the pressure, it wants the original pressure back. And so it's going to convert some of the particles to create even more particles to recreate the pressure that it originally had before the stress was applied, which was a decrease in an increase in volume and a decrease in pressure. Okay, and so it's attempting to get back the original, I don't even know why I put quotes or whatever, original pressure and volume. Okay, so you can think about chemical systems as a creature of habit. And so if it's used to one thing and you create some type of change, it's going to shift in such a way that it's trying to get back to its norm.